So if this is where you don't freak out. Any point on this curve is already defined to be this. True? So then I just make it t squared. So there's r of t. So a couple things can happen at the same time then. I can rewrite the given integram in terms of the components that I know that I'm allowed to use. Just the path I must take. I can only use points on this path. So of course I want to replace the general x and y with the more point-specific definitions, right? So x is what? T, and y is t squared. Which kind of kicks ass, of course, with the 1/3 power. Right, makes it really nice. What goes here?
D.
The magnitude r prime. And what's r prime going to be?
1 plus.
Yeah, it's going to be 1 and 2t. Still a vector. Are we doing so far? Are we okay? So I tried, and we can go over this again, obviously. I try to give you the steps to do for a scalar line integral. Right? You find r, you rewrite your integrand in terms of what you just found. Then you find r prime so you can put it in there. Because what's ds equal to? R prime dt, right? So what's r prime? What's the magnitude of this now? So it'll be the square root of 4t squared plus 1. Right. That part kind of made it a little more of a bummer. But even that part's not going to kill us. dt, and what's my limits? Yeah, x is 0 to 1, x is t, so t is 0 to 1. Cool. So it is a change of variables. So you guys see that? It's a change of variables. And the nice thing is we've taken a 2-variable integral and broken it down to a 1-parameter problem, right? Yeah.
In my book I have x sine y.
Oh yeah, so again, some of you guys might have the earlier version or whatever. Yeah.
So
And does it still have the curve or whatever, or is it a different?
it's the same one.
Same thing, but it has a
x sine y.
no 1/3 power.
No one.
Thank God. Okay. All right.
But even though it's like
So that will still not be that bad, because for you then x sine y, x is t, y is
t squared.
t squared. Looks like a u sub,
Uh-huh.
right? And but you'll still have also the that thing. That's disgusting. Sorry, but
Is there a way to solve it or no?
well, that's disgusting. Thanks, Jeff. That helps me a lot. One thing you can do is if you let u equal to 4t squared plus 1. And this is still not going to help you out a lot. It's disgusting. I think that this is probably typo they messed up on.
Yeah, usually when they do that, it's really hard to solve.
And then just take trace.
But if you let u equal 4t squared plus 1, stay with me for a second. And of course, most of us right now are like, I don't care about that. That's just his problem. Let's hang out with this for a second.
Yeah, I think
Then du is 8t, so then that's the t you can use there. And then to rewrite this, you just solve for t squared. That at least is like a first step. But then you still are in trouble. Because that would become sine of u minus 1 over 4 times square root of u.
2t, 1.
And that's gross. So I personally enjoy the fact, like their decision to change it to that. Unfortunately, you got one before they did that. So
but we won't get one similar to that in these steps.
no.
No.
So let's focus on the one that we should have. You can go ahead and do this one instead. This looks a lot better. So is everybody kind of cool with the steps that we took here? And it is really, I mean, this is pretty much exactly like this in a way. Because we're saying ds equals this times dt. Isn't that like the second step on a u sub? So we're doing basically almost like a t sub, where this is just like this. Okay, maybe. So it is just a substitution step. So I always expect to have ds equal to something times dt. It actually feels more like a trig sub, but let me not make too much of an analogy there. This now from here it's going to be pretty damn easy. Hopefully you agree, because what's this all become here? T. And I got this thing, and thank God I have exactly what I need. You can basically do what we did here, just without any signs in the way. Thank God. You guys could finish that out, right? Yes, that should be the easy step now. But don't freak out when you see, they're not always going to be line segments. They could be curves. So if it's a true circle, we know how to parametricize that. You can let x equal cosine t and y equal sine t. If it's not a circle, if it's something else like that, where they give it to you defined in terms of x and y, make the thing that's by itself, make the other guy t. And then y equals blah t, some function of t. That's what you throw into the place of x and y and change it around. So that I parametricize this parabola as this, from 0 to 1 for t. Yeah. Somebody.
Product rule and chain rule to finish it up.
Well, u sub.
Oh.
Yeah. Can't use product and chain rules for intervals. Yeah. Okay. So the steps for a scalar line interval are figure out what r of t is based on this curve they give you. Right? The curve can sometimes be a straight line, but we still call it a
How would you
curve.
say you do that? If you had a circle, how would you do that? If
So
you had a circle, how would you do that?
Well, if I had a circle, I would just say
X is equal to cosine.
x is equal to cosine t and y equals sine t. And then just define my t so that I get the right.
So
So if they told you it was a part of a circle from, so if it was a part of a circle from like this part of the circle.
I have
So
Yeah.
I tried to do x is equal to cosine t just for this.
Oh, for this guy?
Yeah.
You
Yeah.
could, hell, you could make x equal any function of t you want to, and then y would equal the square of that function. Anything you want to. Right? But here, I'm definitely going to choose let x equal to t. You guys got to think back in your ideas of how to parametricize something. X equal to t, you could certainly choose that, but that's not always the best thing. Here, I wouldn't want to choose x equal to t. Because then y equals plus or minus, oh, screw that shit. Let me do it a better way. X equal to t is not always the best. But when I have something like this, x equals t is the best, period. I could still use sine or cosine. I could use even natural log of square root of t cubed minus cosine t. I could use that. I would want to. Okay. I don't know if you guys quite get me. I could use whatever I want to here. I can make x equal to cosine t. I can make x equal to cosecant t. I can make x equal to 1 over t squared. And then y would be, for that last example, 1 over t to the 4th, wouldn't it? Just the square of the x. But that would make all of this rather gross. And this kind of disgusting. So screw that. So what I'm trying to show you is I could make a problem that's a little harder than this, where x equals to t would actually not be the best. Maybe this would be simpler if I made x equal to t minus 1. And how do you see that? You just kind of start to do it and you go, wait, that would make it easier if I did this. Or if I made x equal e to the t. Maybe it would make this integrand easier to do, and this stuff wouldn't get too gross. Hell yeah, that's the way I would go. But what do you always try first? Try x equal to t. Right, this one definitely is set up for that. Okay, yeah.
So the result now represent the area over of the slice over the curve y equal x.
Yeah, so these are my heights. And I want to know the area of the curtain that's sitting on top. So here's my y equals x squared from 0 to 1 there, right? That's not very, oh well, too bad. Right, here's 1. Here's this. So what this is the area. So now I got to curve my hand. It's the area of the curve where the height is defined by this thing at every point. So at the point 0, 0, the height is 0. At the point 1, 1, the height is 1. And then everywhere in between, the height is whatever. But you have to use points that are on this curve. So you do end up with the curtain area sitting on top, the area of that curtain on top. You end up with this, where of course the height is not always constant, but that's the idea. Not every line integral can be seen physically meaning like that, right? But these line integrals, definitely I can see them as that. That's my height, and I just want to know the area that's sitting on top of that line. And that's actually math 180. That's math 180. Except for us, our line is always the x-axis. Some piece of the x-axis. How much of the curve is over this? What's the area in between those things? You know, that's math 180. The minute you take that axis and say, I don't want that axis, I want some curvy, oh shit, all right? Well, now you got to do this weirdness because you decided to curve what you're integrating over, right? Okay, cool. Cool. It sounds, to me, if I would have just said, now we're going to do integrals where instead of the x-axis, we're going to have this curvy thing underneath us, it sounds like it's going to be insanely difficult. This really is not that hard, you know, especially because they make the integrands here work out so nice, but in general, it's really not that hard. Okay. Any other specific questions before I?
A quick question on 13.5. Number 36, why is it a cylinder and not a sphere?
First and final number
36.
36. So rho equals, oh, okay. Let's see if I can take off here. And of course, so for right now, and I'm not gonna, I think I told you this, I'm not gonna make you memorize the forms and what shapes they are. But even if I didn't give you, I mean, for the homework, you can certainly flip back and look at the, you know, the general forms of things, right?
Right.
But in this case, the first thing I would try to do, I've got to remember, for example, I've got to remember some of my basic conversions. Anybody remember what z is?
Z, cosine.
No, it's for cylindrical. I think this is talking about spherical, right? Yep. Is it? Yes. Oh yeah, we got rho, so there you go, that's a giveaway. So, sorry, say again? Rho. So I know what rho cosine phi would be if I saw it. Unfortunately, cosecant is 1 over sine. So if I try to do something, first off, if I try to multiply both sides by sine, I'll get rho sine phi equals 2. Well, that's not very helpful, right?
I divide by rho.
I divide it by
rho, so you get 1 is equal to 2 cosecant divided by rho, and then.
and rho is what? So if you do that, I'm not sure, let's see, follow you. So if you do that,
Yeah, and then I just replace cosecant with 1 over sine.
okay.
Multiply sine both sides. Once you multiply sine both sides and cosine.
So if you multiply both sides by sine, yeah. So if you do this, rho sine equals 2.
Yeah, the r rho sine is r.
Rho sine is r, good. Because if rho, remember the whole idea that it went back to the submarine. If I do rho cosine is the part on the z-axis, rho sine is the part that actually lies in the xy plane. And that actually is back to just r, right? Now, not officially, because you can't use the letter r really for this, but you can use what r really is. And r is square root of x squared plus y squared. So if you do this, this kind of like, that's r. which is the square root of x squared plus y squared. And then what can you do from there? You remember you started in spherical and now we're trying to go back to just to see what it looks like. You can try to go back to rectangular coordinates. It's not a bad idea because we automatically know what it looks like in the rectangular. And certainly this would be a circle, right, of radius 2.
Where did the R come from again?
Well, so for cylindrical, I mean for spherical, rho is this guy. If I take the projection of him, this piece kind of acts like R. Cool. So that rho sine phi acts like, it is equal to R basically, but I can't use the letter R when I'm in spherical. Truly. So that is R basically. It's the square root of x squared plus y squared.
90 minus phi.
90 minus?
90 minus phi, because phi is with relation to the y-axis.
No, phi is relation to the
Start the z-axis. Oh.
Okay, cool. I can't remember if they put this in the list of shapes they give us. Yeah, okay. So I end up with, and this is independent of which variable really, if I go back to this is independent of z, and that's where it ends up being a cylinder. Because it's just a bunch of circles of radius 2, independent of z, so it ends up being a cylinder. And if you look back at your list, I think they have a cylinder listed there, and it's rho equals a cosecant. Yep.
Back to the graph you drew, which, I guess, corner you could say is the angle phi?
So phi is here. So rho cosine phi, of course, is this. So rho sine of phi would be that. Yeah, cool. Is that cool? So this piece is rho cosine, this piece is rho sine. And that's why rho sine, to really get to x and y, you have to break it up into parts based on theta. That was a part that was kind of gross in the submarine problem a long time ago. So remember, here you got your z is rho cosine, y is rho sine phi sine theta, x is rho sine phi cosine theta. Because here's your r sine theta, here's your r cosine theta. Kind of reverts back to polar once you get into the xy plane. Okay, hopeful. Hopeful. Any other specific questions before I just do a couple of specific things of my own? No, okay. So one of the things we talked about last time was this, how to tell if a vector field is conservative. And the really nice thing, if it is conservative, what is that? What's the immediate mathematical, practical thing I can do then?
Revert to 180.
Revert to 180. So then that means my integral, like this, will just be now really quickly, let me see if you guys get this. If I have a rotational vector field, let me just kind of over accentuate it. You with me? So I have a rotational vector field that's actually would be straight, but let me just go with this. Here's a weird thing. Here's a weird thing that we're not really used to, because all of our Math 180 preconceptions of integrals only apply really when I have a conservative vector field. Because then I can do stuff like this, like we did before. So for example, what would you do here? What would we do here? Yeah, because x squared is the antiderivative of 2x. That's where 2x came from, right? And then I can evaluate it from a to b, so I get b squared minus a squared. That's this, right?
Yeah.
So of course, if f does come from the derivative of something, when I integrate it, I should be able to get that something back. That's the basic idea. And that, of course, is the basic idea when you first learn integration. But the weird thing is, for vector fields, that's only true if it's a conservative vector field. In general, f might not come from some common phi function. So if I just make up a vector field out of nowhere, let me see if I remember the one I made up this morning. Oh, God. That is pretty definitely not going to be conservative. It doesn't come from some phi x is this and phi y, oh hell no. You with me? I didn't have to check that, do I? To check it, you would take the derivative of this with respect to x, with respect to, and that's 0, and that's going to be some funky ass thing. You with me? So that's obviously not going to be conservative, so that's not going to be true. So what that leads to is something very counterintuitive for us. And I know in your mind you're thinking, this whole class is counterintuitive, but if I had a path like this, a true circle, pretend like that's a true circle, in my rotational vector field, and let's say I'm going this way, what would the integral, and what is this? That's the same, it starts at this point and it ends at that point. So in a way that would be like this. Would it?
Yeah.
Not really, because if I do that, I'm being a little misleading, because it's got to be based on t. And t doesn't start from 0 and go to 0. T would go from whatever to whatever. But it is starting at this point and coming back to that point. Is that integral going to be 0? How can you tell just visually? Is it going to be positive or negative? Why? Because the curve, the path I'm taking, lines up with the vector field itself, right? And the whole idea of this integral is adding up all the parts that go along the path I'm taking. Now, of course, if I did this, my integral would become negative, because now it's all pretty much directly against my path. I'm walking against the wind or with the wind. Right? Yeah, the flux, yeah. Gotcha. So for a rotational vector field, it's going to be 0. Gotcha. So that's kind of weird. That means that only if this is conservative will the integral from one point to that same point be 0. Because of course, if it's conservative, then I do phi of the first point minus phi of the second point, and they're the same point. So it's 0. Only if it's conservative. If it isn't conservative, shit, it could be anything. Hopeful as always. Alright. But I desperately want you to get this visual. This is what we're doing. If I'm going this way, I'm adding up all the parts of the vector field that follow my path. In this case, they're all directly against me, so I get a negative answer here. Okay.
So when we are doing integration or differentiation, there's a condition that that we have continuous function, like for example, do the vector field. I mean, how can we guarantee that it is continuous with the vector field function?
The functions that the vector field is defined on, these have to be continuous, especially on the path that you take, right? These functions have to be continuous. Is that cool? Okay, so we have all the same kind of conditions. The functions we're working with have to be continuous. They have to be kind of, in a sense, nice. So considering the fact that we are basically only looking at those functions, which make up like 99% of all functions, that aren't going to go against this whole idea. Let me see, I want to let you into my brain for a minute. How would I make a problem? I want to make a problem where I give you something here, and I know it came from this. It does have that. Because how easy is it to do that just by chance? You have to have phi x and phi. Well, you have to have fy equals gx, and you're not just going to have that happen by chance. It sounds like it's going to be really hard to make that happen. Can you imagine trying to do that and making something that's not silly, like I mean, this would be easy. Yx. Derivative y is 1, derivative x is 1. No, I want a more interesting function than that. I want something a little more interesting, a little bit harder. Right? 'Cause you know me, I don't give you one that easy.
Make a problem that has x and y terms and a x only term and a y only term.
Yeah, but even then I have to make sure that they kind of balance, right? When I take one derivative, am I really going to end up with the same thing? So the easiest way to do it is start with this. Start with the answer. How do I make up a problem? I start with the answer, so I know that it actually works. So if I start, I really desperately want you guys with me, because I want to explain really quickly why, to check for a conservative vector field, why do we check what we check? Why does it make sense that we check that? Right? So if I start off with some phi, let's make it, I wish I could remember what we did this morning, but I won't. Can't remember. I didn't bring it.
I think it was
3e to the, oh yeah, something like that. I like it. So that is a potential function, right? Doesn't mean it has the potential to be a function. It is a potential function. If I want to make a vector field that comes from this, then I just take the gradient. And what would that be? 2xy 3y e to the xy. I love it. Because now y is a constant, so e to the xy, the y comes down. Effectively, chain rule. And then this would be x squared plus 3x e to the xy. So I'm guaranteed now take a step back from what we just did. Let me see if I can do this. If you had to do phi x, of course we just did it. There it is. And then you have to do phi xy. What do you get for phi xy? Like we're doing a problem where we're doing the second derivative test. Remember big D? And you have to figure out the cross derivatives. Oh yeah, 3 to the xy plus 3y squared, right? Not 3y squared, 3yx. There you go. You'll get it someday, Jeff. Would I waste time, and of course I'm giving the answer away here a little bit, but would I waste time doing 5yx?
No.
It's going to be the same thing, of course. We know that. You're with me? This has got to be equal to phi yx. And we can verify that by doing the derivative of this with respect to x, and we're going to get exactly what we just got. You guys kind of with me? Now, if that makes sense, then of course, how do I check to see if this came from a phi? How do I check to see if these came from a common function? I do, that's already x. So let me do that y, and let me do, that's already y, let me do that x, and they have to be equal, like we just said here. So of course this makes sense. That's why, to see if it's conservative, to see if it came from the derivative of some function, so that the integrals will be easy, I just do the cross partials. They have to be equal to each other. So this is nothing amazing. This is just something kind of like, well, duh, that's what you check, because that would tell me they both came from a common phi. Maybe. Now, that leads to something very interesting. And I was debating whether to say anything about this earlier. Think about this. I gave you one earlier that was like, oh wait, let me think. If I give you something like this, we did this one earlier. Is that conservative? Mm-hmm. Yeah, it's really quick to tell because both derivatives would be, well, in this case, 1, right? So here's another interesting one. If I do that, of course, both derivatives are 0. So if I do, now think about that. If I do anything that only has x's in it, and anything over here that only has y's in it, that is automatically a conservative vector field. And it would have come from the antiderivative of this plus the antiderivative of this. That would have been phi. I mean, that's like a, so you can actually make any vector field where this first piece is only a function of x, and the second piece is only a function of y, and kind of the reverse too from that. The reverse would work. Okay, so a few of you guys got what I just said. And that's kind of a little side note. It's an interesting tidbit. But kind of a little counterintuitive. Okay. So anything else specific we want to take a look at? I was thinking about trying to put together another little handout, but I figure we already have enough to try out with this practice test.
You didn't give me the answers to the homework.
What's up?
You didn't give us the answers to the homework.
Yeah, I
Yeah,
did.
you did.
You did?
Yeah, it's on the back.
It's on the back of the quiz.
Oh,
Yeah.
Didn't give us the answer homework.
What you need to do some practice of is like scalar line integral. We did one of those earlier. And the two types, and you'll notice I didn't really put a f dot n problem on the practice test. And I more than likely won't put one on the actual test, just because most of the time we do this guy. Right. So just know the steps involved. So for this one, the steps, what's the very first step when you have a scalar line integral that you have to do?
Rearrange.
Find R. Write that, Jeff. There you go. Find R. Okay. Find R prime, the magnitude. And while you're doing that, you can rewrite integrand using right? Is that cool? Those are the steps. And then you just attack that integral that you have. You guys with me on that? That's exactly what we did earlier. We had to rewrite it. We had to find what R of t is. You had to find what R prime of t was, because you had to put that into the integral. And then we can rewrite the integrand, like we did the xy to the 1/3, rewrite whatever that is. The x piece as the x piece of this, the y's as the y piece of this.
Can we just do one whole
Yeah, sure.
of the scalar and the vector?
Well, so like, let's see. What looks gross in here? Ooh, that looks gross. Might see.
So excited.
So ugly, let's do it.
C is the upper half of the ellipse.
That's usually my response.
Nope, me.
I don't want to do something else. What section? 14.2, right?
Yeah, section 14.2. Yeah.
Thank you.
Yeah. Okay. Now this one is not. No, tell you honestly, I mean, when I saw the word ellipse, I thought it was gross, and then I realized, well, they already did the parameterization for that. So, but can you tell me very quickly which? This is sort of easy to see, but I'm hoping you can understand, because this sounds like a problem I would certainly give. I wouldn't give you the parameterization, I'd give you the ellipse equation, and then you have to parameterize it yourself. The only difference between an ellipse and a circle is that yeah. So along which axis is this ellipse longer?
Why?
Yeah, because it goes out, it's got an amplitude of 4, right? So that's not, so if I give you an ellipse, and it's like this, and this is 3, -3, and this is -1, 1. Couldn't you parametricize that? I mean, it's
Yeah.
Okay.
3 sine t.
and actually this cosine t and sine t, whatever they choose to put there, it would just possibly change those. Are you kind of with me? I don't know if you're kind of with me. So they chose these where they are because at 0, what's x?
2.
2. And at 90 degrees, at pi over 2, x is 0 and y is 4. So you see why they chose this? Because they chose cosine and sine. They actually could have flipped them and just changed their limits on the t. You guys are with me. Because when you do a circle, does x have to be cosine t?
No.
No, it could be sine t. It would just start somewhere different then, wouldn't it? It wouldn't start on the x-axis. It would start up here. Go around. Maybe. All right. Anyways, that's all kind of beside the point at the moment. But to parametricize this thing, I could do the same thing. I would just have, instead of 2 here, I would have 1. Instead of 4 there, I'd have 3. Not a big deal. Right? So this would be the upper part of the ellipse. That's why they wrote it the way they did. But now, what do I have to do now? So my r of t, if I really want to write it out, would be what?
2 sine.
Careful, you get a little ahead of me, that's all right. So there's 2 cosine t,
4
4 sine
sine.
t, and then r prime, yeah. 4 cosine t, okay, cool. So how do I rewrite the inside here? I know that's 0 to pi, they gave that to me. Those nice people. Careful now, careful.
2 cosine 2.
X is here, and y is there, right? Not from your r prime, that's x prime and y prime. I want x and y.
So
2 cosine t minus 4 sine t.
And what's the magnitude now of r prime?
2 sine t squared
4 sine
plus
squared.
4 cosine t.
All that stuff I like.
16
Disgusting, right?
sine squared is cosine.
So I love this problem because it looks like it's going to be almost impossible, but it's not. Let me rewrite this again. ds, let me put that in. 2 cosine t minus 4 sine t. R prime of t.
Well, you can factor out sine squared and cosine squared,
Yeah.
which is 1,
Factor.
and then 4
4
plus.
It's not really factored out, but like take 4 cosine squares t's out.
Yeah.
Put it with that. That would just be 4 then, right? So you can actually rewrite this as, are you guys kind of with me? So really good idea, because then you have one less trig variable in there, right? So if you take 4 of these sine squares, which is all of them, and 4 of these cosine squares, that makes 4, and how many cosine squares are left then? 12. Because 4 sine squares plus 4 cosine squares is 4, of course. Right? That's a common trick to do with ellipses.
You can take a 4 outside.
Yeah, then you can factor 4 out as a 2. No, a 4, Jeff, there you go. No, a 4, Jeff, there you go. Okay.
It's funny how you talk to yourself.
Yeah. Alright, so then you get, let me just do this. So out comes a 2 from here and a 2 from there, so there's a 4 out here. Okay, cool. Let you guys think about that for a minute. That's a good general thing to do with an ellipse, yeah.
How'd you do that sine squared trick?
What do you got on the side?
Oh, here. Square root of 4 sine squared plus 16 cosine squared. I can write 4 sine squared plus 4 cosine squared plus 12 cosine squared. Is that, let me stop right there. If I really wanted to, I could do that. Because 16 is 4 plus 12.
Yeah.
But then this
Oh, gotcha.
is 4, yeah. Cool. So let me see. So now the new stuff is over. Now this is back in possibly 180, depending on the method you want to use here, or 280. Put it up here real quick. Well, the weird thing is, the thing about this, real quick, just to throw something out there. If you try to do a straight up U sub, what would happen?
But you're not going to get anything minus anything.
Well, what are you going to get, just to see?
You're gonna have negative 6 sine t.
Yeah, negative 6. Well, really careful. So 2 comes down makes 6.
6 cosine.
times cosine t times the derivative of the cosine, which would be negative sine t. Cool.
You cannot cancel. So why don't we get it n to the root first? Get that cosine 2 sine t to the root and then follow it inside and
That's you can do.
So square this to put it inside. Okay, that might work. Possibly. You'll get some cross terms. That's another thing to try. All right, so what he's saying is if you do the square root of this squared, you can throw it inside. Is that what you're saying to do? Okay. That's something you could try.
Distribute, break into 2 separate intervals.
If you break it into 2 separate integrals, then you have a cosine times this and a sine times this.
yeah, sometimes that will work. Would they use substitution? And cosine.
Well, that one,
will they use?
please split it up and you sub because it wasn't.
Well, no. Remember, u sub, no matter what I do here, u sub is going to require this. Which, you know, if you wanted to, what's the trig identity I can use here? It's not going to be very useful, but it's not going to really do anything for us, so it doesn't really matter. But remember, 2 sine, cosine.
So about parts.
You can do it by parts, possibly, yeah.
Where'd you get the 4? I thought you had a 2 outside the square root. The 4 in front of the.
Oh yeah, here's another factor of 2.
Oh, there you go.
And then that factor of 2, yeah. Okay. All right, but let me be careful here. So I didn't necessarily pick this one because I knew I was going to get to this point. I just picked it so I can show you how to set it up. Let's kind of let go of this for right now so we can focus more on the process instead of this particular interval. Is that cool? But I mean, these are the kind of things, if I gave you one that was like this is the kind of stuff you'd have to start thinking about and trying. And that, of course, is what I understand, that if you pick the wrong way to go, the time you spend on that way is wasted. But that's why part of what you have to do as a math student is become better at telling earlier when it's not going to go anywhere and letting it go, right? And maybe letting that problem go and doing some other problems and coming back to that problem. So it's all about time management on a test. So for right now, let's just focus on, we set the interval up, now it's just a question of what method to use to finish it, and that's old stuff. So is that cool if we kind of let this go for right now?
Yes.
Okay. So is there another specific problem you want to work on?
This is 14.2. What about 14.3?
Oh, real quick thing about when the word conservative comes from the fact that with these fields, if I do integrate from the point, come back to the point, if it's a conservative vector field, that interval is going to have to be what? 0. Because the 5b minus 5b at 0 at that same point. Is that cool? So that's why, that's really where the word conservative comes from. If I have a conservative system, it doesn't bleed off any energy and no energy comes into it. It stays in the same state. So if I integrate all the way around and come back to the same point, it's 0. Yes?
Just like conservative physics, where you have friction.
That's exactly right. So like if you send current down a wire and it comes back to itself here, it's not going to be the same because it's ohmic losses along the way. It's not a conservative system. It's losing some of that energy to heat, right? So it wouldn't be the same when it came back, so they wouldn't match up. The beginning wouldn't match up with the end, so it's not conservative. Good. So that, just in case you're wondering why the hell they call it conservative vector field, it's not because there are liberal vector fields. I appreciate the Thanks. So, do you want to do like an example problem? We can do.
It's going to be on the test.
Yes.
Let's do this. Well, I'll tell you what. Let's do this because I want to. We just did one that was a scalar line integral, and we got it set up just to a point where we got to figure out how to integrate that piece. Let's do, before we get into the conservative vector field, let's just do a general vector field integral, right? So this could be Let's see, let me take one out of here, keep myself straight. No, no. Here we go. They're not very interesting.
No, I think he just said he wouldn't put.
Switch down first. Alright, let's see. Remember, you guys ever do this one or not? I think so.
Something like
It's number 36 in 14.2. Uh, 2.2 to 10.10. So this is in section 14.2. This is before we knew about conservative vector fields. So for scalar line integrals, the first step is what's R. Then you can kind of do two things at once. You can rewrite the integrand in terms of the x of t and y of t pieces of R, and you can find R prime to find the magnitude of R prime. So for scalar vector field, for scalar line integrals, it's integral f. No, get out of it. The integral of what am I trying to say here? You can do it, Jeff. Yeah, there it is. This thing, whatever function they give you, right? So this would be the ds. It's whatever function they give us. I rewrite the pieces of this in terms of what x and t and y and t are from the R I get. Those are the steps we take. For a vector field line integral, the difference is the R prime doesn't really show up the same way it does here. Because the magnitudes, I don't know if you remember, cancel out when we do that whole process. So if I want to find the integral f dot t ds on this curve, step one is still, find r of t.
vector field line integral, right?
I'm going to give you a second, try to figure out what that r of t is.
Is it a trick? Is that already like a vector, a unit vector form? Like,
It's not really a trick. It's a good point. This is not quite a unit vector because it's
It's unit vector multiplied by 1 over r.
exactly cool. But it's not quite a unit vector because it's not a 1/2. It's a 3/2. Is that cool?
Do you want to make it a 1/2?
You can't just make it 1/2. No. I like that though. It's not a bad idea. But no, don't do it. So what do you get for r of t? What's the first thing you got to figure out to get r of t? Yeah, if you take 10 minus 2, 10 minus 2, you get 8, 8. That's the direction. So an r of t would be 2 plus 8t and 2 plus 8t. Now I want to tell you that you could do r of t is t, but then t has to go from what to what? 2 to 10. Not a big deal. You see, you've got some leeway here. T would have to go from 2 to 10. Here, t goes from what to what? 0 to 1, exactly. You guys with me so far?
0 to 1.
Because of the way that we have defined it. This is the first point. If I add 8, 8 to it, I get to the last point. So I only have to have 1, 8, 8 to get to 10, 10. Whereas here, if it's t, I start at 2, 2, I add 1, 1. I add 1, 1. I add 1, 1. I add 1. So I got to do it a lot more. Okay, how are we doing so far? Yes?
How'd you come up with a t plus 8t?
Just pick a point.
Oh, sorry. So this is my 8, 8 vector, right?
Okay.
So I have to start at 2, 2 and add t times 8, 8.
Okay.
And then I just gotta put it together. Cool. So then what am I gonna replace in here? So here I can rewrite, here's my f. let me do this on the side. F will now be what? And do you see why, do you start to see why? This is my point from earlier. Is it better to do it this way, do you think, or this way? Because here, what would x and y be? X and y would both be t. Whereas here, x is 2 plus at, y is a little bit more disgusting than it has to be. So this one is a really good example of one that is very simple to make an easier R of t. Because it's 2, 2 to 10, 10. So TT works beautifully. Right? They're not all going to be that easy just to look at and tell, so you can always do it this way. So now this is going to be, if I use, are we cool with using, instead of this, using that definition?
Yes.
Thank you. So if I rewrite f, what do I get? Yeah, t over tt over t squared plus t squared, so 2t squared, so 3 halves.
Yeah, which is.
Which you can simplify a little bit. Cool.
Professor,
Yeah.
how'd you make a TT?
So if I go for the point 2, 2 to 10, 10. Well, this is saying that what has to be true then? If this is a true line segment, the slope has got to be 1, right? And x has to equal y. It's basically a piece of x equal to y. This is a piece of x equal y. So what's the easiest way to parametricize that? X equals t, y equals x, so y equals t. Yeah. If you don't see that, you'd have to use this, and that would make this a little bit ugly, not too terrible. It wouldn't make it terrible. Like,
So you can equate x and y based on the slope of the points that are given?
based on the fact that x equals y in every point on that line segment. So that's the definition of this line segment is x equals y. From what to what? From 2 to 10. That makes it a line segment. Cool. All right, so there's my f. What's my r prime? Yeah, 1, 1.
So the second point of.
So then what I do for this integral is I do exactly what it tells me to do. I do this dot product. So what's the dot product between those two things going to be? Let's see if we can do this. This thing is a common piece to the whole thing, right? So it'll be 1 over 2t squared to the 3 halves times. Now what's the dot product between tt and 1, 1? T plus t, so 2t. Which kind of looks nice, doesn't it? Something's going to happen there. So the main things to get from this kind of problem are, what are the steps involved? Don't get too concerned about the specifics about this problem, but what are the steps involved? Find R. And I don't care if you're doing a scalar or a vector field, you use those elements of the R to rewrite the given function. Be it a vector field function or be it a scalar function. Scalar value function. You with me? You always find R first and you use it immediately to rewrite what you're given. You find R prime, now this is where it's going to be, to me, would be the most difficult thing with this process. For scalar line integrals, I need R prime, magnitude. For vector field integrals, I need the dot product between f and R prime. I don't need a magnitude of R prime. What's kind of inherent in this dot product? Magnitudes, right? So that they do end up being something sort of the same. So how do I get this? This piece here is there. TT dotted with 1, 1 is here. And now you can just integrate that. What's going to be from to?
0 to 10.
2 to 10 in this case. Good. So that's a good example of what I was talking about the other day. It's only going to be 0 to 1 if you do this thing to it. And in this case, I really don't want to do this thing to it. Much easier way to do it.
If we do it like 2, 4, 10, 12, could we do like t and t plus 2?
Yeah, you can always do this. All right, let me show you something right now.
It's like find the relation
You
between.
can always do this. Watch. Do it again.
like 2 for 10, 12.
T and T plus.
What's the y equals, the slope would be 8 over 8, the slope would be 1, x minus 2 plus 4.
Okay.
So y equals x plus 2. So if x is t, y is t plus 2. I think that's what you said.
Oh, yeah,
Same thing.
yeah. Okay.
Because the definition of every point on the line is the y piece is twice, 2 more than the x piece, yeah.
Okay, and in that case, where are we going from 2 to? We are going from 2 to 4 to.
In this case, it would still be 2 to 10 because x is t.
Oh yeah, okay. So we go with the okay.
So you go with what x is doing. Yeah. Yeah.
With vector line, it's now f dot dr, and we're no longer using ds.
Well, now be careful. It still is ds. It's just that it's integral f dot t ds. Let me do this one more time, real quick. Let me see, what do I need here?
So you're now bringing in magnitude of r prime.
I want to show you. I want to show you how you are. Real quick. This piece is this. Is this cool? That piece is that. This is r prime over the magnitude of r prime. That's the tangent. That's what it's defined to be. So those go away. And then this, that's why I end up with f dot r prime dt, which I very often I'll write like this without thinking about it. So that's, is that cool? This piece would be this.
Yeah. Where'd you get the 2t? Where you went from the numerator, the vector tt to 2t? Yeah, right there.
Oh yeah, so tt f dotted with r prime. So what's tt dotted with 1, 1?
Yeah.
T plus t, 2t. Cool. And now the integral looks disgusting, but it's not that bad. It's just a power rule, right? Yes.
What's the denominator?
Oh, it's still right here. It's just when you plug in what's x, t, what's y, t, what's t squared plus t squared? 2t squared.
It didn't dot product with a 1, 1, 2.
Yeah, because if I put it in there, it would just be underneath both, and then I can take it back out anyway. So I just kind of wrote it by itself there. Is that cool? So I factored it out first instead of factoring it out last. Yeah. All right, and then this integral, do you guys agree with me? Sometimes I understand this entirely. When you learn new stuff, you get to something that's old stuff, and you're like, what the hell now? Because you think, no, it's old stuff. You simplify this, it's a power rule, integrating that's easy. Not even going to do it because it's easy.
What do you get?
Just to make sure you guys, maybe I won't.
1 over 8.
What do you get? I can pull out 2 to the 3 halves. Is that cool?
Yeah.
And actually, let me be careful.
Well, 2's canceled, so.
It would
Well,
be
careful so you
t
don't
cubed
cancel.
inside.
Oh, no, because it's everything to the 3 halves.
2 over.
So I'll get t squared to the 3 halves is t third, thank you. And times 2t. So I have another 2 that can come out here, not going to worry about that in a minute. 2 to 10. That 2 came out, so I get 1 over t squared. That's an easy answer. Right? So simplification of that should not be the problem. It's just that I notice, no matter what level of math I teach, I always notice when a student hits a part of the problem that's old news, they think of it as, well, it's got to be new. The whole problem's new. This has got to be, no, it's old. Simplify, integrate. The minute you get everything in terms of t, it's math 180, basically. Hell, you can put x's in there if it makes you feel better. It's math 180 now. Simplify, integrate, done.
So I feel like it's just because you can do this in your sleep, but whereas we got to think about it, and you do it quickly,
Now,
and we're just so
that's the point I'm trying to make. This stuff here, I'm not going to gloss over this stuff. I'm not going to say you should be able to do this easy because this is new shit. This, I feel very comfortable saying, in your sleep, you do that. If not true, then that's a problem. That should be like, thank God.
Variable, it'll probably throw me off, like, what the? But it's like, dude, it's the same thing.
So, let's look at conservative vector fields now, real quick. Oh, you're playing. In fact, look at that vector field we just had. how do you test to see if this is a conservative vector field?